Constraints are mechanisms provided within the SQL standard to maintain the consistency and integrity of a database, and at the same time enforce certain business rules in the database application. There are 5 different types of declarative constraints in SQL that can be defined on a database column within a table, and they are as follows: primary key, not null, unique, check, foreign key. The primary key constraint is used to maintain the so-called entity integrity. When such a constraint is declared on a column of a table, the DBMS enforces the following rules. The column value must be unique within the table. The value must exist for any tuple, a record, or a row of data that is to be stored in the table. That is, the column cannot have a null value. For the student table in our university database, for example, we have SID as the key attribute. As a normal business rule, all students must have a valid and unique ID number as soon as they are enrolled. Thus, the SID column must have a unique value and cannot be null. To enforce this business rule, we can have the primary key constraint declared on the column when creating the student table. One way to do this is as shown below. In the above SQL statement, the constraint is declared by using the keywords constraint and primary key. A column definition clause with such a constraint declaration is called a column constraint clause. PK_student is a user-defined name for the constraint. It is optional, but when defined, it can help the database designer and user to pinpoint the violation of this constraint. The reason is that, when this particular constraint is violated, the DBMS will generate an error or warning message which includes the constraint's name. A usual convention for defining a primary key constraint's name is PK_table name. There is an alternative way to declare the primary key constraint, as shown. It be3 that a table can have at most one primary key constraint, and it is actually optional. A table does not have to have a primary key constraint. However, it is rare that a table be created without such a constraint, because tables usually do have a primary key. The not null constraint is imposed on any column that must have a value. In the student table, for example, the attributes dname and level can have this constraint declared on them to reflect the application requirement that whenever a student is enrolled, he or she must be assigned to a department and be at a certain level. To declare the constraint on dname and level, we can use the following SQL statement to create table student. You may have noticed that the constraint on dname has been given a user-defined name and an _student_dname, while the one on S-level has not. It is optional to name a not null constraint. Unlike the primary key constraint, it does not make much difference whether or not you choose to define a name for the constraint. In Oracle, when the not null constraint is violated, the system will generate an error message. However, this message will not include the name of the not null constraint, even if one is defined. Also notice that, when a constraint is not to be given a user-defined name, the keyword constraint is not used. The same applies to other constraint definitions. The unique constraint is the same as the primary key constraint, except null values are allowed. In the student table, for example, the semail attribute should have this constraint. The reason is that, according to the university's policy, a student may or may not be given an email account. However, when one is given, the email account name must be unique. By enforcing this constraint on semail, the DBMS can ensure that different students will not be allowed to have the same email addresses. For those who do not have an email account, the semail column can have null values. To declare the unique constraint on semail, we can use the following SQL statement to create table student. Again, an optional user-defined name, UK_student_semail is given to the constraint. This is a good practice in Oracle because when the unique constraint is violated, the system will generate an error message containing the name Similar to the primary key constraint, the constraint's name helps pinpoint the violation. Declaration of a basic check constraint. The check constraint defines a discrete list of values that a column can have. This list of values may be literally expressed within the constraint declaration, or may be defined using a mathematical expression. In the student table, for example, a student must be at a level between 0 and 3. To impose such a constraint, the create statement for the student table will be like as shown below. Notice two things in the above create statement. First, the check constraint can be declared in a column constraint clause and concatenated with other not null, unique, and/or primary key constraints. When a column constraint clause is concatenated, there is no separator between the different constraints, just a comma after the last constraint. Second, the check condition can include logical connectors such as and, or. Thus, it is possible to define a complex condition. Complex check constraints. It is also possible to create a check constraint that is constructed from multiple columns of the table. In this case, because it applies to more than one column, the constraint must be declared with a table constraint clause rather than a column constraint clause. For example, instead of declaring two check constraints on S level and D name respectively, we can use a single constraint called ck_student_validity as follows. This create statement will create the same student table as the earlier statement that uses two separate check constraints. A foreign key is a column, or a set of columns, attributes, that links each row in the child table containing the foreign key to the row of the parent table containing the matching key value. The foreign key constraint enforces referential integrity, which means that, if the foreign key containing a value, that value must refer to an existing, valid row in the parent table. In our university database, for example, SID and code are foreign keys in the record table. Notice that SID and code together form the primary key for record as well, and record has two parent tables, student and module. For a row in record, there must be an existing student row with the same SID value in student, and a valid row in module with the same code value. Otherwise, the referential integrity is broken. One important implication of this is that when using foreign key constraints, the parent tables must be created before the child tables, and the parent tables must be populated before the child tables are populated, in order to avoid constraint violations. It is important to bear in mind this required order of doing things when undertaking practical work involving foreign key constraints. The following SQL statement can be used to declare the foreign key constraints on SID and code when creating the record table, as shown. It can be seen from the above example that the foreign key constraint can be given an optional name. In the example, fk_record_SID is the name for the constraint on SID. To define the name, the keyword constraint must be used. Otherwise, it is omitted, as in the case of declaring the constraint on code. The keyword's foreign key defines which column or columns is the foreign key column to be constrained. The keyword references indicates the parent table. By declaring and enforcing the foreign key constraint, the DBMS can ensure that the referential integrity is maintained in both the child table and the parent table. In the child table, the DBMS will not allow any insert or update operation that attempts to create a foreign key value without a matching candidate key value in the corresponding parent table, as indicated by the references clause. In the parent table, the DBMS ensures that appropriate actions are taken for any update or delete operation that attempts to change or delete a candidate key value that is being referenced by some rows in the child table. The kind of actions that can be taken are user-definable. They are cascade, set null, set default, and no action. This action can be triggered by either a delete or a update operation. When a parent row is deleted, all its child rows are also deleted. This action can subsequently be applied to each child row deleted because such rows may themselves have a candidate key that is used as a foreign key in some other tables. Thus, this action may be executed in a cascading manner. The cascade option can be specified in SQL as follows. In this example, when a student row is deleted from the student table, all his or her records will also be removed from the record table. When the candidate key value is changed by an update operation, the foreign key column in the child table are set to the same new value. Similar to cascade by delete, such update actions can be carried out in a cascading manner to the child tables of the child table, and so on. For example, when a student's identity number, SID, is changed, all his or her records in the record table should have the new SID value to replace the old. In Oracle, such an action can be defined by creating a trigger to be discussed later. When a row is deleted from the parent table, all its child rows will have their corresponding foreign key column set to null. This option is only valid if the foreign key column allows null value, that is, it has neither the primary key constraint nor the not null constraint. Similarly, when the candidate key value of the parent row is changed, all its child rows may have their corresponding foreign key column set to null. Again, this option is valid if and only if the foreign key column allows null value. The set null option can be specified in Oracle by creating corresponding triggers. By having this option, the operation of deleting the parent row or updating the candidate key value in the parent table will set the corresponding foreign key column in the child table to its default value. This option is only valid if the foreign key column has a default value specified. Again, in Oracle, this option can be implemented using appropriate triggers. This is the option by default. If there is no other option specified, the DBMS will reject any delete or update in the parent table that may affect rows in the child tables. Any such illegal attempt to break the referential integrity will raise an error message in Oracle. Once created, a table's definition can still be changed using the alter table command in SQL. Different DBMS implement alter table differently, providing more or less functionality than that specified in the SQL standard. In Oracle, the following operations can be carried out on a table using appropriate alter table statements. Add a new column, including a constraint declaration for that column. Modify an existing column's type with certain restrictions. Modify an existing column's constraint definition with certain restrictions. Add a new constraint to an existing column. Drop, remove an existing constraint from a column. Suppose we now want to create a new column in the record table to store the date on which the mark was obtained. The column is to be named exam_date and can be added in the following way. The SQL keywords that should be used are highlighted. If there is an application requirement stating that the exam date must not be earlier than the 1st of January, 1998, in order for the mark to be valid, we can include a check constraint as well when creating the new column. In this case, the following SQL statement is used instead of the previous one. The constraint is given a name, ck_record_date. The system function to_char is used to convert exam_date into a string so that it can be compared with 980,101, representing the 1st of January, 1998. Other constraints can be specified in the column constraint clause in a similar way. Using the alter table command, we can modify the type definition of a column with the following restrictions. If there is data except null present in the column, then the type of this column cannot be changed. The type definition can only be changed if the table is empty or all values in the column concerned are null. If the type definition is changed on a column with a unique or primary key constraint, it may potentially become incompatible with the data type of a referencing foreign key. Thus, the alter table command should be used with caution. The following SQL statement changes the data type of SID in the record table to number 9. The original type was number 5. Notice that SID in record is a foreign key referencing SID in student, which still has the type number 5. However, number 9 and number 5 are compatible. This alter table operation is allowed. If we attempt to change SID to be of type varchar 2, 5, it will be rejected because of incompatible data types. There are a number of possibilities for modifying a constraint definition. If a column has the not null constraint, it can be changed to null to allow null values, and vice versa. For example, the email column in the student table did allow null values. If we wish to change this, the following SQL statement is used. Notice that the above operation is valid if and only if the table is empty, or the email column does not have any null value. Otherwise, the operation is rejected. For other existing constraints, that is, unique, check, and foreign key, if they need to be changed, they have to be removed first, drop, and then new ones add. New constraints, such as unique, check, and foreign key, can be added to a column. In our university database, for example, we may add a unique constraint on sname in the student table. As a result, no students can have the same name in the database. In the record table, if we want to ensure that mark is always less than or equal to 100, we can add a check constraint on mark as follows. In the lecturer table, dname is a foreign key with a link to the department table. If we did not declare a foreign key constraint on dname when creating lecturer, we can add it now using the following statement. All the keywords in the statements are highlighted. Notice that we have given names to all the newly added constraints. They will be helpful when constraints have to be dropped. The alter table drop command is used to remove an existing constraint from a column. This operation is effectively to delete its definition from the data dictionary of the database. Earlier, we have added a unique constraint, named UK_student_sname on sname in the student table. It prevents any students having the same name. Obviously, it is not practically useful because it is always possible that some students may happen to have the same name. In order to remove this constraint, we can use the following SQL statement. Notice that, in order to drop a constraint, its name has to be specified in the drop clause. There is no difficulty if the constraint has a user-defined name. However, if the user does not give a name to the constraint, when it is declared, the DBMS will automatically assign a name to it. To remove such a constraint, the system-assigned name has to be found out first. It can be done in Oracle, but it causes some unnecessary trouble. This may be another incentive to define a name for a constraint when it is declared. A trigger defines an action the database should take when some database-related event occurs. Triggers may be used to supplement declarative constraints to maintain database integrity, enforce complex business rules, audit changes to data. Because of their flexibility, triggers may supplement database integrity constraints. However, they should not be used to replace them, that is, the constraints. It is worth mentioning that, in order to create a trigger on a table, you must be able to alter that table, and any other table, that may subsequently be affected by the trigger's action. The type of a trigger is defined by the following three features: event, level, timing. Event. It refers to the triggering SQL statement, that is, insert, update, or delete. A single trigger can be designed to fire on any combination of these SQL statements. Level. It refers to statement level versus row level triggers. The level of a trigger denotes whether the trigger fires once per SQL statement or once for each row affected by the SQL statement. Timing. Timing denotes whether the trigger fires before or after the statement level or row level execution. In other words, triggers can be set to occur immediately before or after those triggering events, that is, insert, update, and delete. Stored procedures in Oracle. Some sophisticated business rules and application logic can be implemented and stored as procedures within Oracle. In fact, triggers are a special type of procedures associated with tables and invoked, called upon, by pre-specified events. Stored procedures, containing SQL or PL/SQL statements, allow one to move code that enforces business rules from the application to the database. As a result, the code can be stored once for use by different applications. Also, the use of stored procedures can make one's application code more consistent and easier to maintain. This principle is similar to the good practice in general programming, in which common functionalities should be coded separately as procedures or functions. Some of the most important advantages of using stored procedures are summarized as follows. Because of the processing of complex business rules may be performed within the database, significant performance improvement can be obtained in a network client-server environment. Refer to the client-server unit for more information. Since the procedural code is stored within the database and is fairly static, applications may benefit from the reuse of the same queries within the database. For example, the second time a procedure is executed, the DBMS may be able to take advantage of the parsing that was previously performed, improving the performance of the procedure's execution. By consolidating business rules within the database, they no longer need to be written into each application, saving time during application creation and simplifying the maintenance process. In other words, there is no need to reinvent the wheel in individual applications when they are available in the form of procedures. Functions and packages in Oracle. In Oracle, a procedure is implemented to perform certain operations when called upon by other application programs. Depending on the operations, it may not return any value, or it might return one or more values via corresponding variables when its execution finishes. Unlike procedure, a function always returns a value to the caller as a result of completing its operations. It is also worth mentioning that a function may be invoked by code within a procedure, and a procedure may be called from within a function. In Oracle, groups of procedures, functions, variables, and SQL statements can be organized together into a single unit, called a package. To execute a procedure within a package, one must first specify the package name, followed by the procedure name, as shown in the following example. This is an example to show how to use a procedure within a package. In the example, DBMS_output is the package containing a number of procedures relating to displaying message on the screen. Put_line is a procedure within the DBMS_output package that can take a string of characters, that is, the text in the single quotes, and output them onto the screen. Note that, in order to use Oracle's DBMS_output.put_line procedure to display text on screen, you need to execute the command set server output on once in the SQL plus environment.